Hello, welcome to our semiconductor education program. This is Vincent Chang. So in this lecture, we're going to continue our learning on some of the basic characteristics of semiconductor materials. In the past, I have spent the time on explaining the nature, the characteristic of the intrinsic semiconductor. So basically from two perspectives. The number one is from bond model. The other one is from the energy band, the diagram, the concept of band gap, the valence band, and the conduction band. So in this lecture, I'm going to start to explain the extrinsic semiconductor. So extrinsic semiconductor, part one, donors and acceptor. Donors and acceptor. So let's start with the bond model of the intrinsic silicon. You know, the valence electron and two valence electron forms a bond called covalent bond. So at absolute zero temperature, because so the valence bands are occupied. No conduction ability. So the material functions as an insulator. Right. But at higher temperature, at the room temperature, because the lattice vibration, the covalent bond is broken. So some of the bond is broken and generating the electron hole pair. So this kind of process is called thermal generation. All right. So of course, if you go the backward of the generation, so one of the electrons go back to the seed, and then electron is dead. The seed also doesn't exist. So this is called the reverse process of the thermal generation is called recombination. All right. So today we're going to talk about the impurity. All right. So there are two types of impurity can be doped, can be put into the semiconductor material. Now, number one, the first one is called N-type. The other one is called P-type. Let's start with the N-type. We know the semiconductor material like the silicon germanium, they are column 4. They are located in column 4. So on the right-hand neighbor, you see the column 5. So for example, in silicon material, for silicon, so most commonly used dopant are phosphorus and arsenic. Phosphorus and arsenic. For example, if it's phosphorus, it's 15. The atomic number is 15. So 15 equals 2 plus 8 plus 5. Red, blue, and green. So first orbit, 2. The second orbit, 8. The outer orbit, there are 5. The 5 valence electron. 1, 2, 3, 4, 5. In the history, so in the early stage of the semiconductor, when we developed when semiconductor industry is developed, the most traditional technique is called diffusion. All right, we put the dopant into the material and the atom will diffuse. But more advanced technology is called ion implantation. So it's the implant. That's why the title I said the N-type impurity implanted. So we implanted the dopant, the impurity atom, into an intrinsic semiconductor material. So now you see an intrinsic, right? So now let's imagine through a machine, the manufacture process, the impurity dopant got implanted into the intrinsic silicon. And then what happened? Usually the impurity atom will take the original spot of one silicon atom. So it's kind of like the substitution, right? It will sub one of the silicon atom's spot. So that spot was surrounded by the 4 nearest neighbor, right? So now it's 5. So valence electron, there are 5 valence electron. So the phosphorus, the impurity atom, is neutral. So the neutral equals the -5 plus the positive 5. Okay? So the positive 5 represent what? You can put down this on your note. The positive 5 represent positive 15, which is the atomic number, minus 10. All right? Okay, I don't think I need to belabor the detail because I explained this in the previous lecture when we talk about the intrinsic silicon. All right. So now, as long as the temperature is enough, so usually around room temperature is good. And then it's kind of like the 5 kids. The first parent carries the 5 kids, but 4 are settled with a pair. Okay, it's stable because bonding means the stable. All right, but the 5th one is kind of rebellious, right? Or you can say it's kind of loosely bound. The bond, the tight, the relationship is kind of loose. So once you give the 5th kids, the 5th electrons a little bit thermal energy, usually this will be satisfied at the room temperature. You will say goodbye to the parent. Bye. So I become free. I become a free electron become a conduction electron. Right? So in this case, when this happened, we said ionization. This is the process of ionization. As I mentioned, this kind of ionization usually is satisfied. It's automatically happens around room temperature. So this tells us the parent, the phosphorus, donate, give. So donate the system, the material system, an additional conduction electron. So this parent, this phosphorus, is called the donor. It's called the donor. So remember, the donor atom is neutral. It's the neutral atom. But when the gift is sent out, or when the rebellious electron, the rebellious kid, say goodbye to the parent, and then because the rebellious kid carried -1, so the parent body becomes not neutral anymore because you lose 1, right? So look at your right hand side. So positive 5 plus -4 equals what? Positive 1. So that unneutral parental body is called the donor ion. All right? It's called donor ion. So the donor ion is carry positive 1. Donor ion carry positive 1. Remember this, very, very important. Okay? So neutral donor atom on your left, the positive donor ion on your right. So now let's talk about the p-type impurity. So starting from the column 4, so if you look at the left, column 3, you see in semiconductor, in silicon technology, most commonly used the p-type silicon, because aluminum is usually used for the conduction, for the metal. So number 1 is boron, the other one is gallium. All right? So boron and gallium. So if it's boron, 2 plus 3, that's it. 2 plus 3, the atomic number is 5. So the 3 means what? The outer orbit carries the valence orbitals. There are 3 electrons. Valence electrons sit in the valence orbital. So 3. So if we just use the manufacturing, we try to we try to implant the boron into the silicon, and then this is what you see. So 3, right? So 3 neutral. So the neutral boron equals the -3 plus the +3. And then And then what? I got to get my image back. Okay, sometimes I just, so focus and think about my brain run really fast, right? So I forgot to pull my image back. Excuse me. All right, next time I try to not do this. So now it's the p-type impurity implanted, right? And then what? This is 7. So if you ever learn the chemistry, what state is most stable, most secure? 8, right? 8. So now it's 7, which means what? Which means there's a strong desire to get one more. To get one more electron from anywhere within the material, right? So it provides this boron donate a spot, an empty seat, but it has a strong desire to get one more. So once this happens, if we get one more electron to take the spot, then what does that mean? That means the system, the parental body, release a positive hole, release an empty spot. So that empty spot can be illustrated, can be depicted as a positive charge carrier, which is called the hole. So you can say we donate a hole, okay? So the N-type is called donor, and P-type is also called donor. They get confused. So in semiconductor, we always sit in the perspective of an electron, right? So if you donate an electron, then it's called donor. But if you donate a hole, it's not called donor, because it's called acceptor. So accept is sit in the perspective of an electron, accept an electron. So it's called acceptor. So when this happens, when what happened? When ionization happened, when a positive charge carrier is released, then the parental body again carries a charge. What kind of charge? What kind of charge? Positive 3 plus negative 4 equals negative 1. So this kind of negative 1 charge in the parental body is called acceptor ion. All right? Acceptor ion. So 4. Neutral donor ion. Neutral donor atom. Positive donor ion. Neutral acceptor atom. Negative acceptor ion. So make sure you capture this. This is very, very important. In the future, when I talk about the interaction, the interface between the p-n junction, for the p-type semiconductor, because we put a lot of acceptor, right? For the n-type, we put a lot of donor. So in the p-type, because we put a lot of acceptor, we release a lot of hole. So the hole is the majority carrier. For the n-type, abundant electron. Electron is the major force for the conduction. But through the interaction, which I will explain in a later lecture, we'll talk about the p-n junction dynamics. And then you will find out when the hole diffuse into the n-type semiconductor, the parental charge will be exposed. So what exposed? Negative acceptor ion. The negative acceptor ion. So same thing, because on the right-hand side, I will explain the detail in the future, right? So, but let me just quickly just give you a quick summary. So the electron concentration is very high on the right-hand side, and then the electron will diffuse to the other side, will diffuse to your left-hand side. So when the electron leaves the anti-semiconductor, the charge will be exposed. What kind of charge? Positive donor ion. So in the depletion region of a p-n junction, the left-hand side of the depletion region carries negative charge. So that kind of negative charge is called the negative acceptor ion. On the right-hand side of the depletion layer carries positive charge. That kind of positive charge is called donor ion. So the p-type ion carries negative charge. P means positive. Okay, don't get confused. This is why I slow down and try to emphasize the importance of this part. Okay, so the engineers, the students got confused all the time around this. So make sure you get this. Again, donor atom, neutral. Donor ion, positive. Anti-impurity is positive. All right? And then acceptor ion, atom is neutral. Acceptor ion is negative. Make sure you get this. See you in the next lecture. Thanks for watching.